Welcome to the deep dive. We're here to cut through the noise and really get into the heart of the big shifts happening in tech.
That's right.
And today, we are plunging into something truly fascinating, I think, and definitely fast-moving: AI agents.
Mhm.
Now, these aren't just, fancy chat bots. We're talking about software systems that can actually make decisions, break down tasks, even use tools by themselves.
Yeah, proper agency.
Exactly. And look, this isn't some distant sci-fi thing anymore. It's already a significant economic force. We're seeing projections that it could jump from, what, about $5.2 billion just last year
Yeah, late 2024
to
figures.
nearly $200 billion by 2034. That's huge growth.
It's astronomical.
And get this, more than half of large IT companies, they're already actively using these agents. It's a really fundamental change in how we interact with software, isn't it?
It absolutely is. And well, for quite a while now, the sort of core intelligence, the brains behind most of these modern agents, has come from large language models. Right,
LLMs.
the big ones. The big ones.
Yeah.
So they've been seen as the generalists, the all-rounders. And the industry has poured massive investment into this idea, this operational model.
We're talking serious money.
Oh, yeah. Something like $57 billion surged into cloud infrastructure just this year alone. And that's all based on the assumption that LLMs are, well, the only game in town for agent intelligence.
Okay, so if that's the established view, this is where our deep dive today takes a really interesting, maybe even surprising turn.
Hmm.
What if? What if these incredibly powerful generalist LLMs are actually overkill for a lot of what these agents need to do?
Right. What if they're too much?
Exactly. What if there's a different approach, maybe a much more efficient one that kind of challenges the whole basis of that huge investment?
Okay.
So today, our mission is really to unpack this compelling argument we found in our source material, that small language models, SLMs, aren't just, an alternative. They might actually be the future of agentic AI.
A pretty bold claim.
It is. So we'll explore what SLMs really mean in this context, why they're being pushed as the next big thing, the arguments behind it, and crucially, what this potential shift could mean for the whole AI landscape.
Sounds good. And I think to really get our heads around this, we probably need to start by defining our terms.
Right.
What do we actually mean by SLM and LLM when we're talking about agents? Because the definitions used here are actually quite practical.
Yeah, that's a good point. So when our source talks about an SLM, a small language model, they're defining it in a really functional way. It's basically a language model that's small enough to fit onto a standard consumer device.
Like your laptop or phone.
Exactly. And it has to perform its tasks, its inference, with low enough latency that it's actually practical for a single user's agent requests. It needs to be responsive.
Okay, so size and speed on everyday hardware.
Pretty much. And as a sort of rule of thumb for where we are now, say 2025, most models under about 10 billion parameters are generally considered SLMs in this context.
Okay, under 10 billion. And so an LLM is just anything bigger.
Essentially, yes. An LLM is any language model that doesn't fit that SLM definition. Too big or too slow for that local single-user scenario.
Got it.
And when we mention agents or agentic systems, we're kind of using those terms interchangeably. It's the software that has agency, or the system components, where these language models, whether SLM or LLM, act as the core intelligence.
Right, the focus is on the language model's role within that system.
Precisely. So with those definitions clear, let's dive into the core position, the main argument from our source, why SLMs are being championed as the future here. It really seems to boil down to three key contentions.
Okay, what are they?
First, the argument is that SLMs are, maybe surprisingly, already powerful enough. Like they have sufficient capability for the specific language modeling needs of these agentic applications.
So V1, principally sufficiently powerful. They can do the job.
Exactly. They're not just good enough, they're sufficiently powerful. Then the second point, V2, focuses on operational suitability. The source argues SLMs are inherently better suited for actually being used inside agentic systems compared to the big LLMs.
Interesting. Better suited how? We'll get into that, I assume.
We will. And the third pillar, V3, is maybe the most immediately impactful, the economics. SLMs are argued to be necessarily more economical, more cost-effective for the vast majority of agentic uses, basically because they're smaller.
Right. V3. Necessarily more economical, powerful enough, better suited, and cheaper. That's a strong trio.
It really is.
And the underlying why here is quite interesting, I think, because, okay, LLMs, Yes, they have using general knowledge, great conversational skill.
Undeniably impressive, yeah.
But the source makes this really compelling case that most of the individual tasks an agent performs, well, they're actually quite repetitive. They're often narrowly scoped, maybe not even conversational at all.
Like what kind of tasks?
Well, think about an agent needing to just parse a specific data format, like JSON, or extract one piece of information from text, or maybe generate a really standard templated response.
Okay, lots of small focus jobs.
Exactly. And in those very specific situations, the argument goes, SLMs don't just scrape by. They're often actually better.
Better because?
Lower latency, so faster responses, reduce memory and compute needs, which is huge, and critically, significantly lower operational costs, all while performing perfectly well enough for that specific narrow job.
Okay, so you're trading that massive generality you might not need for efficiency. You definitely do.
Precisely. And this has big implications for how we might build these AI systems, right?
Yeah.
It points towards a fundamental architectural shift.
Towards what the source calls heterogeneous agentic systems.
Exactly. Heterogeneous meaning mixed. The idea is, sure, for those really tough problems, the ones needing deep general reasoning or, complex open-ended chat,
Right, the heavy lifting.
you would still call on an LLM, but do it selectively, sparingly even.
Okay.
But for the vast majority of the agent's tasks, the everyday stuff, SLMs would be the default. They'd be the specialized workhorses.
So it's like a modular toolkit.
Yeah, a best tool for the job approach. You combine the super efficiency of SLMs, for most things, with the brute force generality of LLMs only when you absolutely have to.
That makes a lot of sense architecturally.
It does. And the detailed arguments supporting this vision, well, they're pretty persuasive when you lay them out.
Okay, let's get into those details then. Argument A1. SLMs are already sufficiently powerful. This feels like a big claim given the hype around LLMs.
It is, but the evidence is mounting. We're seeing this dramatic speed up in SLM capabilities. The performance isn't just creeping up, it's getting steep. They're closing the gap on much larger, older models really fast.
Can you give some examples?
Sure. So take Microsoft's Phi 2. It's only got 2.7 billion parameters, which is tiny compared to the big players.
Right.
Yet it achieves performance on things like common sense reasoning and code generation that's on par with models 10 times its size, like in the 30 billion parameter range. And it runs about 15 times faster.
Wow, okay. 15 times faster is significant.
It's huge for agentic tasks where latency matters.
Yeah.
Or look at NVIDIA's Nemotron H family.
Yeah.
They have models from 2 up to 9 billion parameters.
Still firmly in SLM territory.
Definitely. And they're achieving instruction following and code generation accuracy that's comparable to dense 30 billion parameter LLMs.
So similar capability, much smaller package.
Exactly. And maybe even more striking, there's this DeepSeek model, the R1 Distill Quinn 7B. It's actually outperformed some very large proprietary models like Claude 3.5 Sonnet and even GPT-4o on specific common sense reasoning benchmarks.
Outperformed GPT-4o on reasoning.
On certain common sense reasoning tasks, yes, according to the benchmark cited.
That's really something.
It is. And it's not just reasoning. Salesforce has an 8 billion parameter model, XLM28B, that's hit state-of-the-art performance specifically on tool calling that's getting the AI to use external tools or APIs correctly.
Which is critical for agents.
Absolutely. And it's surpassing models like GPT-4o and Claude 3.5 in that specific area.
Okay, so specialized strength. But can you moose them further?
Yes. That's another key point. You can enhance SLM capabilities at inference time when they're actually running. Techniques like self-consistency, where the model checks its own work multiple times, or tool augmentation.
Like the Toolformer example.
Exactly. Toolformer, only 6.7 billion parameters, was shown to outperform the original GPT-3, which was a monster at 175 billion parameters, simply by being really good at using external APIs.
So it's not just raw size, it's how you use it and maybe specializing it.
That's the core takeaway here, I think. For agentic apps, the capability needed for the task is the constraint, not necessarily the sheer parameter count. These examples really show SLMs have enough reasoning power for a huge chunk of these tasks.
Making them viable, but also maybe more suitable.
And often more efficient. Which brings us neatly to argument A2. SLMs are more economical in agentic systems.
Right, the money argument. Let's talk numbers.
Okay, the cost savings can be pretty dramatic. A typical 7 billion parameter SLM compared to a large 70 or 175 billion parameter LLM, well, it can be anywhere from 10 to 30 times cheaper to serve.
10 to 30 times. Cheaper, in what sense?
In terms of latency, so faster response. In terms of energy consumption, which is huge for sustainability and cost. And in FLOPs, the raw computation needed. That's a massive difference.
It really is, especially if agents are making millions or billions of calls.
Exactly. And the savings aren't just in running the models. Think about fine-tuning them.
Adapting them for specific needs.
Right. An SLM can often be fine-tuned in just a few GPU hours. That means you could potentially add a new behavior or specialize it for a new task literally overnight,
Compared to LLMs.
which can take weeks and significant compute resources to fine-tune properly. That agility, that speed of iteration, is incredibly valuable for agent development.
Okay, faster iteration, lower running costs. What else?
Well, edge deployment becomes feasible. You can actually run these SLMs locally on consumer-grade GPUs. Think NVIDIA's ChatRTX platform.
Running on my own machine.
Potentially, yes.
Yeah.
Which gives you real-time inference, it works offline, and crucially, it offers much better control over your data, especially if it's sensitive.
That privacy angle is increasingly important.
Hugely. And there's also this idea that SLMs might be just more fundamentally efficient. Like a smaller percentage of their parameters contributes to the cost without actually improving the output quality for a given narrow task. Less waste, perhaps.
Less computational overhead for the result you need.
Kind of. And all this efficiency leads towards that more modular design we mentioned, like building with Lego bricks.
Instead of one giant sculpture.
Exactly. You scale out by adding small, specialized expert SLMs rather than just scaling up one massive monolithic LLM. The resulting systems tend to be cheaper to run, faster to debug, easier to deploy.
And probably better suited to the sheer variety of real-world tasks agents need to handle.
That's the argument. They're just a better fit for that diverse reality.
Which leads perfectly into the next point, A3. SLMs are more flexible.
Yes. Because they're smaller, the costs associated with pre-training them from scratch or even just fine-tuning them are way lower.
Makes sense.
So it becomes much more affordable and practical to actually train, adapt, and deploy multiple specialized expert models. You could have one for scheduling, one for data extraction, one for drafting emails, tailored to specific agentic routines.
Okay, specialization becomes easier. What's the bigger implication there?
Well, this is where it gets really interesting, I think. This flexibility could lead to what the source calls the democratization of agents.
Democratization. How so?
If you lower the cost and complexity barriers to building and deploying capable AI models, well, then more people, more organizations, smaller companies, even individuals can participate.
Right. It's not just the tech giants with massive GPU clusters.
Exactly. And if you have a more diverse population of creators building agents, the resulting pool of agents is much more likely to represent a wider range of perspectives, different needs, different values.
Which could help tackle things like bias in AI.
Potentially, yes, by having more diverse inputs and applications. And it could also just foster much faster innovation, simply because more people are experimenting and building.
That's a powerful idea. More accessible AI leading to more diverse and innovative AI.
It's a compelling vision.
Okay, another argument, A4. Agentic applications expose only very narrow LM functionality. What does that mean exactly?
Think about how agents actually work. They don't just have a casual chat with an LLM. They usually give it very specific instructions, maybe a strict template. They choreograph its steps.
They're directing it very precisely.
Very precisely. They're essentially fencing off the LLM's vast general capabilities and forcing it to use only a small, specific skill set for that particular task.
Okay.
So the argument is, if you're only ever using this tiny slice of the LLM's potential, why use the whole massive, expensive LLM? A smaller, specialized SLM, fine-tuned for just that narrow skill, could probably do the job just as well, if not better.
And much more efficiently and flexibly.
Exactly. You're using a scalpel instead of a sledgehammer for fine work.
Right. And that ties into A5, doesn't it? About behavioral alignment.
It does, very closely. Especially when agents need to interact with code or other systems. Think about tool calls or needing output in a strict format, like JSON or XML, so another program can parse it.
Yeah, that has to be reliable.
Absolutely crucial. You cannot have the models suddenly deciding to use a different format or adding conversational chit-chat. It breaks the whole workflow.
Right. Hallucinating the wrong format is a killer.
Totally. So a specialized SLM trained specifically to output only that one required format is often much more reliable and preferable to a general-purpose LLM that you have to constantly coax and constrain with complex prompts just to keep it in line.
Specialization leads to reliability for these structured tasks.
That's the idea.
Okay, and A6. Agentic systems are naturally heterogeneous. We touched on this, the modular approach.
Yeah, the architecture itself encourages using different models. You have the freedom to choose. Maybe you do use a powerful LLM for the top-level planning, the root agency figuring out the overall
A
strategy.
conductor of the orchestra.
Right. But then for all the individual subordinate tasks, the
Yeah.
actual playing of the notes, you employ specialized SLMs.
Okay.
Or you could even go fully SLM.
Mm.
Maybe one SLM is fine-tuned to be really good at understanding the user's conversational intent, and another is an expert at executing a specific API call sequence, and another handles summarizing results.
Building the agent out of specialized components.
Exactly. Mix and match based on the need.
And the final argument, A7, is about data. Agentic interactions generate data for improvement.
Yes, and this is a really neat, almost self-reinforcing point. Every time an agent uses a tool or calls any language model, SLM or LLM, to perform a subtask, that interaction, the prompt, the response, whether it worked, is potentially a high-quality data point, assuming, of course, you handle it securely and anonymize it properly.
Right, privacy first.
Always. But if you collect that data, you get this constant stream of real-world examples of exactly what you need the models to do.
Which is perfect.
For fine-tuning those specialized expert SLMs, it makes improving them a natural, ongoing part of just deploying and running the agent. It's not a separate, massive effort. It's built into the life cycle.
That's clever. The system generates its own improvement data.
It creates a really virtuous cycle.
Okay, those are some incredibly strong arguments, A1 through A7, painting a really convincing picture for SLMs taking over large parts of the agentic world.
It's a compelling case.
But, no major shift happens without pushback or alternative perspectives. What are the counterarguments? What do the LLM proponents say?
Right, let's look at the other side. A common alternative view, AV1, is basically that LLM generalists will always have an edge because of their superior general language understanding.
The bigger is better for understanding arguments.
Essentially, the points usually are LLMs demonstrably perform better on broad language benchmarks. Their capabilities improve predictably according to scaling laws, more data, more compute, bigger model, better results, and they might possess this sort of semantic hub.
A semantic hub? What's that?
It's a theoretical idea that larger models develop a more integrated central understanding of concepts, allowing them to connect and reason across different domains more effectively than smaller specialized models might.
Okay, so better general understanding, scaling laws favor them, maybe this deeper semantic integration. How does the source rebut that?
Quite effectively, I think. First, on scaling laws, they point out that many studies assume the model architecture stays the same as you scale.
But SLM development is using different architectures.
Exactly. We're seeing innovation in SLM architectures that yield better performance for their size, which kind of sidesteps the standard scaling assumptions. Second, remember that flexibility point.
Fine-tuning easily.
Right. SLMs can be quickly fine-tuned for specific tasks to get the reliability you need. General scaling law studies don't really account for that targeted adaptation. An LLM might be better in general, but a fine-tuned SLM could be better for the specific agentic task.
Good point. And the semantic hub.
The argument there is, remember how agents break down problems? They decompose complex goals into simpler subtasks.
Right.
So the actual calls to the language model, the SLM invocations, are often on these much simpler, narrower sub-problems. In that context, a grand, integrated semantic hub doesn't really offer much practical advantage. You don't need world knowledge to parse JSON correctly.
So the LLM advantage might be irrelevant for many agent tasks.
That's the counter-argument.
Okay, what's another alternative view, AV2, about economics?
Yeah, this one argues that, okay, maybe SLMs are cheaper per token, per call, but the sheer economy of scale you get from massive centralized LLM inference farms might outweigh that.
Like, it's cheaper overall to run one giant factory than lots of little workshops.
Kind of. Critics might say it's harder to manage the workload efficiently across lots of different expert SLMs. You need specialized infrastructure, maybe specific talent. The overhead costs could eat up the per-token savings.
That sounds plausible. Is it true?
Well, the source acknowledges this is a valid consideration, and the exact balance might depend on the specific situation. They concede the jury might still be out on the absolute economic winner in all cases.
Yeah.
But they also highlight that things are changing fast. There are big improvements happening in inference scheduling software. They mention NVIDIA Dynamo as an example that makes managing these diverse workloads much more flexible and efficient than before.
So the tech for managing distributed SLMs is catching up.
It seems so. And they also note that the general costs for setting up infrastructure keep falling. So while it's a fair point, the economic tide might still be turning towards SLMs. even considering scale.
Okay, interesting. And the last alternative view, AV3, it seems more pragmatic.
Yeah, AV3 basically says, look, maybe both worlds, one dominated by LLMs, one by SLMs, are equally possible technically. But the reality is the LLM world has a massive head start.
Inertia.
Exactly. Industry inertia, huge investments already made, tools built around LLMs. It's just the established way right now.
And the source acknowledges that.
They do. They say this is a distinct possibility. The LLM dominance could just continue because it's already rolling. However, they maintain their core position, that the combined weight of all those SLM advantages, A1 through A7, power, economy, flexibility, is strong enough that it can plausibly overcome that inertia and flip the script.
So it's possible, but not guaranteed, that SLMs will win out over inertia.
It seems to be an open question, but they argue the advantages are compelling enough to bet on SLMs.
Okay, so if the arguments for SLMs are so strong and the counter-arguments have decent rebuttals, why isn't this shift happening faster? Why aren't SLMs everywhere in agents already?
Yeah, the source identifies some key barriers, B1 to B3, that are currently slowing things down.
What's B1?
Massive upfront investment. We talked about the billions poured into centralized LLM infrastructure.
Right, the $57 billion.
Those huge capital bets have sort of locked in the current paradigm. Tools get built for LLMs. Cloud services are optimized for LLMs. It creates an ecosystem that favors the incumbent, and the potential of decentralized SLMs gets kind of neglected.
Path dependency.
Pretty much. Then there's B2, the focus on generalist benchmarks.
How is that a barrier?
Well, SLM development often still aims to compete on the same broad benchmarks as LLMs, like reading comprehension across many topics or general conversation.
Trying to beat LLMs at their own game.
Sometimes, yeah. The issue is, while an SLM might not top the leaderboard against a giant LLM on those general tests, it might absolutely crush it on benchmarks specifically designed to measure agentic utility.
Like how well it performs the specific tasks agents actually do.
Exactly. Things like tool use accuracy, following complex instructions, generating structured data reliably. Because the research and development often focuses on the general benchmarks, we might be undervaluing or underdeveloping SLMs for the areas where they naturally excel for agents.
Interesting. We're measuring them against the wrong ruler, potentially.
It could be. And finally, B3 is simply a lack of popular awareness.
They just don't get the headlines.
Not like the big LLMs do, no. LLMs are flashy, they generate amazing text and images, they capture the public imagination. SLMs, being smaller, more specialized, often designed for back-end tasks, they just don't get the same marketing push or press coverage.
Even if they're incredibly useful and maybe more suitable for many industrial uses.
Right. So developers or companies might not even realize that a highly capable SLM is a viable or even superior option for their agentic application.
Okay, so inertia from investment, maybe focusing on the wrong benchmarks, and just less public buzz.
Those seem to be the main hurdles identified.
But the good news, according to the source, is...
The good news is that these seem to be practical hurdles, not fundamental flaws in the SLM approach itself.
They can be overcome.
Plausibly, yes. Things like NVIDIA Dynamo are already chipping away at the infrastructure inertia, B1. The benchmark problem, B2, is getting more recognition in the AI community, so focus might shift. And lack of awareness, B3. Well, that tends to solve itself as the economic and performance benefits become undeniable and more widely known.
Success breeds awareness.
Pretty much.
So if an organization is convinced or at least intrigued by this potential shift, how do they actually make it happen? Is there a roadmap?
Well, the source actually outlines a potential LLM to SLM agent conversion algorithm. It suggests the very way agents work makes this transition quite feasible.
Okay, walk us through it. Step S1.
S1 is secure usage data collection. Crucial first step. You need to instrument your agent system to log the interactions that don't involve direct human chat. So calls between agent components, calls to language models, tool uses.
Logging the internal workings.
Exactly. Log the prompts, the responses, which tools were called, the latency, and critically do it with strong encryption and anonymization right from the start. Privacy and security are paramount.
Absolutely. Okay, log the data securely. Step S2.
S2 is data curation and filtering. You collect enough data that the source suggests 10,000 to 100,000 examples is often enough to start fine-tuning small models. Then you meticulously clean it. Remove any potentially sensitive information, maybe using automated tools, maybe careful paraphrasing. Got to have clean, safe data.
Got it. Data logged, data cleaned. S3.
S3 is task clustering. This is where you analyze that collected data. You use unsupervised machine learning, clustering algorithms to find recurring patterns, what kinds of requests keep coming up, what operations are common.
Identifying the distinct jobs the agent is doing.
Precisely. These clusters help you define the specific, specialized tasks that you could potentially offload to dedicated SLMs. Like intent recognition might be one cluster, data extraction from emails another, generating SQL queries a third.
Okay, define the tasks. Now S4.
S4 is SLM selection. For each task cluster you identified, you now choose one or maybe a few candidate SLMs.
Based on what?
Based on their known capabilities, how they perform on relevant benchmarks, agentic ones hopefully, their licensing terms important, and their deployment footprint. How easy are they to integrate, what resources do they need, etc.
Picking the right tool for each defined job.
Exactly. Then comes S5, specialized SLM fine-tuning.
This is where the magic happens. Kind of, yeah. You take the task-specific data you curated earlier, and you fine-tune your chosen SLMs on it. Techniques like LoRa or QLoRa are mentioned. These are efficient ways to fine-tune models without retraining everything from scratch, saving time and money.
What about knowledge distillation?
That's mentioned too. You can sometimes train the SLM to mimic the outputs of the larger LLM it's replacing. This can help transfer some of the nuance or capabilities of the bigger model to the smaller one.
Whatever. Okay, models selected and fine-tuned. Are we done?
Not quite. Step S6 is iteration and refinement. This isn't a one-off process.
Ah, the continuous improvement loop.
You got it. You need to periodically retrain your specialized SLMs with new data that comes in from the ongoing agent operations. Back to step S1. This keeps them performant, helps them adapt to any changes in how the agent is used, and ensures they stay effective over time.
So, collect, curate, cluster, select, fine-tune, iterate. Seems like a solid process.
It provides a clear pathway, at least conceptually.
To make this more concrete, did the source give any real-world examples, like specific agent systems and how much LLM usage could potentially be swapped out?
Yes, they looked at a few prominent open-source agent frameworks to estimate the potential.
Oh, interesting. Like what?
Okay, first, MetaGPT. This is a framework that tries to simulate a whole software company using multiple agents roles, like product manager, engineer, QA tester.
Wow, ambitious. Where do LLMs fit in?
They're used for things like role-specific actions, planning, generating code, writing documentation.
And the SLM potential.
The analysis suggests that for the more routine code generation, handling structured responses, maybe basic planning steps, SLMs would be well-suited, their estimate. Around 60% of the LLM queries in a system like MetaGPT could potentially be replaced by specialized SLMs.
60%? That's substantial.
It really is. Okay, next example, Open Operator. This one is more focused on workflow automation, making API calls, orchestrating tasks, maybe interacting with databases.
More operational, less conversational.
Generally, yes. And here, the thinking is, SLMs could easily handle simpler command parsing, generating templated messages or API requests, things like that.
And the estimate for Open Operator?
Around 40% LLM query replacement potential. The LLMs would still be valuable for more complex multi-step reasoning or if there's a tricky conversational flow needed, but a lot of the standard work could shift.
Okay, 40%, still significant. One more.
Oh, yep, Cradle. This one's designed for controlling GUI applications, basically, looking at the screen and figuring out where to click, what to type to operate regular desktop apps.
General computer control. Sounds complex.
It is, but a lot of GUI interaction involves repetitive workflows, right? Clicking the same sequence of buttons, filling similar forms.
True. Once you learn a workflow, it's often repeatable.
Exactly. So SLMs would likely excel at executing these pre-learned or repetitive GUI sequences. The potential replacement estimate here, a whopping 70%.
70%? Wow.
Yeah, suggesting that maybe the LLM is needed for the initial understanding or learning the workflow, but specialized SLMs could handle the bulk of the actual execution.
So these case studies, they really connect the dots, don't they? They show this isn't just theoretical. In real complex agent systems, the potential to swap out LLMs for SLMs seems significant.
Definitely. Across these examples, you're seeing estimates from 40% up to 70%. That points to a huge potential for cost savings, speed improvements, and maybe even better performance on those specific tasks.
What an incredible deep dive this has been. It really feels like agentic AI is on the cusp of fundamentally changing white-collar work, and maybe much more.
The potential is definitely there.
And it's just fascinating to think that a major catalyst for this huge transformation might actually be something as pragmatic as saving money. The drive for expense savings and more sustainable AI infrastructure could be what pushes us towards these more efficient, specialized SLMs.
Economics is often a powerful driver of technological shifts, isn't it?
It really is.
And it's worth remembering, too, that the authors of the paper we've been discussing, they're actively inviting feedback. They put their position out there and are asking the community to contribute, to critique, to build on it.
So this isn't a closed book. It's a live conversation happening right now in the AI world.
Absolutely. It's an active, evolving debate at the very forefront.
Which brings us to our final thought for you, the listener. As you mull over all this, consider this. If SLMs really can make AI agents significantly cheaper, faster, and more accessible, what does that future actually look like?
Yeah. What happens when powerful AI isn't just in the cloud, but can run effectively on your own devices, or within much tighter budgets for businesses or researchers?
What does that unlock for innovation, for creativity, for how we live and work every day?
The implications feel pretty massive.
They really do, and it seems like this conversation is only just beginning.